Okay, this video is on another work done, calculating work done. And this is going to focus on moving liquids. I think the last one we focused on pulling up chains or pulling up a banner, but now we're going to move liquids. So once again, remember that work is just the product of force times distance. So we have to figure out the force, and we have to figure out how long that force is being applied, over what distance. So in this case, we're going to empty this water tank. And so we have this little inside information that water is 62.4 pounds per cubic foot. So if I want to figure out the force, I need to take 62.4 pounds per cubic foot and multiply it by some cubic footage, because that would give me the force it would take to move that cubic foot of water. And once again, when we're looking at integrals, now of course the reason why we need integration in this case is because not all the water is moving the same distance. The water at the bottom is going to move 15 feet. The water at the top is going to move hardly anything at all. So the distance is changing. So just like the chain problem and the banner problem, our distance is going to be pretty easy. If we call this bottom thing 0 and this top thing 15, and we'll say this is my x variable, or you could say height or depth or whatever, then we know that the distance that the water is going to travel, each little section of water that's going to travel, is 15 minus x. So the water at the bottom is going to move a full 15. The water at the middle is going to move about 7.5. The water at the top is going to move hardly anything at all. So that's why we do 15 minus x. Okay. Then the next step is to figure out the force. Well, the force, once again, is going to be 62.4 pounds per cubic foot times cubic feet. But remember also, since we got this distance thing set up, we need to grab a volume of water that's moving roughly the same distance. And of course that's going to look kind of like the old disk method. We're going to put these little disks in here, right? And we know that all that water is going to move roughly the same distance. And all of this water is going to move roughly the same distance. So it's kind of like we froze the water and took slices of it and just slid them up one at a time. And so we're going to take the volume of each one of those little slices and multiply it by 62.4. So we'll put the 62.4 out here. And now the volume of water is, of course, is going to be, this is just a little short cylinder. So we're going to do pi times r squared times a little bit of height. In that case, a little bit of height would be dx. Now the question is, what is the r squared? Well, we know the r is just 4. So we'll put a little 4 in there. So if we set this up correctly, of course this is going from 0 to 15, because that's the distance pumped, the water pumped. We can multiply 4 times 4 squared to be 16. So 16 times 62.4, that's going to be 998.4, and we'll move the pi out front too. And so then here we just have 15 minus x dx. And we can calculate that. Of course, you'd evaluate the integral and it'll tell you how much work was done, and that the units would be foot pounds, because we're multiplying pounds per cubic foot by cubic. This would be cubic feet, so that'd leave me just pounds, and of course this is measured in feet, so it'd be foot pounds. Okay, now let's do the same exact problem, but let's say instead of unloading the entire tank, there's only 10 feet of water in the tank. Okay, so the distance is still going to be 15 minus x, because this bottom guy is still going to go 15. That guy is going to go 5. We're still going to have a dx, still going to have a 998.4 pi out front here, because none of that stuff changed. The weight of water is still the same. We're still moving up little slices of water. The only thing that's going to change here is I'm only going to integrate from 0 to 10 instead of from 0 to 15 like we did before, because we only want to integrate where the water is. Okay? And give another slight variation. Let's say we have the same exact tank, it's full again this time, but we're going to pump it up 3 feet above the top. So there's no water in this tube. The water just goes up the top, but we're going to pump it up through the tube and out. So that means that's not going to change the weight of water. It's still going to be 998.4 pi. It's not going to change the limits of integration because I'm still integrating from 0 to 15 because that's where the water is. But what it will change is the distance, because now when I'm at 0 here, I'm actually pumping at 18 feet. And when I'm at 15 feet, I'm actually pumping at 3 feet. So what we're going to put in here is 18 minus x dx. Remember, the dx is part of the volume formula over here. So changing the height that we pump to changes the distance formula, but changing how much water is in there changes the limits of integration. So that's a kind of important little thing to pay attention to. Now, of course, if the shape was different, then our volume formula would have been different, right? Let's say that for some reason we have a square water tank. I don't know if they make those, but let's say we did. So that means the little slice that I'm pumping looks like that with a little bit of thickness, right? Let's say it's still 15, and let's say the thickness here is 4, and we're just pumping it to the top and out. Okay, so we're still going to have 62.4. This time we won't have any pi because the formula for this little slice is just going to be 4 by 4 by dx. So that would be 16 dx. And the distance is still going to be from 15 minus x. And we're going to pump from 0 to 15. So that would be, I think I already did 16 times 2. Yeah, that would still be 998.4. No pi, because there's no pi in our formula. Going from 0 to 15. And that would be 15 minus x dx. So it's just little variations on the pumping thing. I'm pumping, so this would be pumping liquids, like you could pump water or muddy water or sludge or gasoline or whatever. And of course, the thing that's going to change is the shape of the thing you're pumping it through, and possibly the water or the weight of the thing you're pumping. So that would, of course, affect the force. But there's a lot of problems that are like this where you're just moving liquid. All right.